Oh boy, this was a pain in the ass. This crashed far too many times. Anyway, one set of poles. That's what to actually do. Get an Earth radius. If they just press enter, it defaults to 6371. Convert it from kilometers to meters, which you do by multiplying by 1,000. For those who didn't know that. You know who I mean. Observer height in meters, and if they just press enter, it defaults to 2, as if you're standing on a couple of telephone directories, or a big brick. Observer offset in meters, how far off the center line you are. If you just press enter, you just stay on the center. Field of view in degrees, which you get. If it's 0, it jumps to the degree equivalent of 2 radians. And then we get a scale factor, which is 640, half the width of the screen, divided by the radian equivalent of your field of view over 2. In other words, the default field of view is 2 radians, but if you put in a different number, it will give you that many degrees width across the screen. This is a 5x4 screen, not a 4x3 for anyone who cares. Dimension, also known as an array, called pole, percent saying it's of integers. 8x3, it has 8 entries, each of which has 3 values. And relative pole, same size. Procedure, also known as a routine or a function. Make pole, this is something that's further down, saying, it's called make pole, do whatever it does. I'll show you that next. And then for values of an integer called distance, from 50 to 1/20th of a radian, that being how far around the Earth you can see from Mount Everest, approximately, in steps of 100 meters. Procedure, draw the pole, next distance, and then print done, wait for him to press a key, go back to the start. If we list up to 1500, we can see what make a pole does. It just defines all those coordinates. You have 1, 2 and 3 on the left side at 101 meters left, 4, 5 and 6 on the right side of the pole at 99 meters left, and 7 and 8 are the pole itself, 100 meters left. 1 and 4 at this end, 6 and 8 at the far end are only 9 meters above the ground, where 2 and 5 in the middle are at 11 meters, the top of the pole is at 12, the bottom is at 0. Distance forwards is 0 at the near end, 1 and 4. It's 50 in the middle, 2, 5, 7 and 8, and it's 100 at the far end, 3 and 6. And then to actually draw it, you work out values for relative pole. These are the relative coordinates of the pole at the current position, because we're adding distance each time, which is worked out like this. For each of 8 positions on a pole, its the relative x-coordinate is the actual x-coordinate minus the viewer's offset. This is a negative number, and this is a negative number. You're going to get a smaller negative number. If this is a negative number, and this is positive, you're going to get a bigger negative number, which is less than, but it's a negative number of greater magnitude. If this is a very large positive number and this is a small positive number, you're going to get a slightly smaller positive number. So it is how far right of the observer that part of the pole is. Relative pole y-coordinate, vertical position, is radius of the Earth plus its height above the surface times the cosine of how far forward it is plus the distance, which is increasing with each time we draw it, divided by the radius, minus how far up the observer is, height above surface plus radius of surface. And the relative position of that point on the pole forwards is that same radius from the centre of the Earth times the sine of that angle. Messy, huh? Next day, go through all 8 points, and then move to 1, draw to 2, draw to 3, move to 4, draw to 5, draw to 6, move to 2, draw to 5 to do the cross piece on the top of the pole, move to 7, draw to 8 to do the vertical part. And all of this arctan, moved 640 to the centre of the screen horizontally, plus the scale factor we worked out earlier, times the tangent. So by default, scale factor is 640, so this is half the screen, times the angle in radians whose tangent is how far right of the observer that point on the pole is, divided by how far ahead of the observer that point on the pole is. It's just the angle you'd get drawing a map of this, looking top down. And a vertical coordinate on the screen of the middle of the screen, plus the same scale factor, times the angle in radians, whose tangent is how far above the observer that point on the pole is, divided by how far ahead of the observer that point on the pole is, which is what you get drawing an orthographic side projection of this. And the same thing is done for all of these. So by default, standard Earth size, observer height in meters, 2 meters above the water, no offset, field of view 2 radians, and it's going to draw this. Left wire, right wire, crossbar, pole. Left wire, right wire, crossbar, pole. Speed, fixed speed 100 times, zoom off into the distance. You'll notice that standing 100 meters to the right of this line of poles, with a wide-angle view,
well, it looks flat to me.
Same Earth radius, but this time we'll move the observer up 100 meters. And we'll move closer to it, so we're looking along above it instead. There the wires are underneath us, stretching off into the distance. Again, go to 100 times simulation speed. Just make it try to run 100 times faster than the BBC Micro could have done this.
And it still gets pretty boring pretty fast.
But this time, well actually for comparison, let's have really huge Earth. That's good. Let's have a huge Earth. Just, 6, 3, 7, 8, 1. Equatorial radius times 10. Observer height in meters. And let's just go for default again. And it doesn't look any different, does it?
Still looks flat to me.
But let's do an impression of Soundly. Normal Earth size. Let's go to 10 meters elevation. So the observer is now between the height of the crossbar on the pole and the height of the sagging middle of the wire. And I'm going to move the observer 96 meters left. It's just to the right of this line of poles. Actually, if we really want to be soundly, I should move to 103. So it's just to the left of this line of poles. And we are going to zoom right the heck in to a 4-degree field of view. Really needs higher resolution to be able to see exactly what's going on. Well, golly gee whiz, Batman. It sure looks curved to me now. It's almost as if the way I worked out perspective there actually works, isn't it? It's almost as if we globeheads do actually know what perspective is and how to calculate it. Yeah, almost.